Let's go ahead and consider what happens when we look at a few different data sets. So let's start off with the bird colonies. Here's your data. If we just go ahead and do a least squares regression and look at r and r squared, we get our least squares regression line to be this. We get r to be this, and we get r squared to be this. So 56% of the variability in the new birds can be explained by the returning birds. Now, we know it's a negative r, so we have a negative slope, which is the case. If we look at our scatter plot, we have this. If we draw in our least squares regression line, we have this here. Question is it a good fit? It doesn't look bad. R was reasonable. There's a lot of spread outness, variability, sorry about that. Let's look at your residual plot. Are they pretty much randomly distributed on either side of your horizontal axes of 0? Yes, so it's a good fit. Let's take a look at the icicle run. Here's your data. The least squares regression line is right here. R is quite high. R squared is also high. Looking at your scatter plot, we have this. And it's like, oh, it looks pretty good. When you look at your residuals, though, there's a definite pattern. It's not randomly distributed on each side. So therefore, your data is not linear. It's a curved pattern of some sort, and therefore you would not want to use your least squares regression line. Let's take a look at this one here. Here's your data set. Here's your correlation. R, once again, is fairly high. There's your regression equation. Your scatter plot looks pretty good. We look at our residuals randomly distributed on either side. Taking a look here, here's our data. We do our least squares regression. Still looks pretty good, fairly high R. We look at our scatter plot. Oh, it's a definite curve pattern, so we don't want to use your least squares regression line. When you look at the residuals, it shows up even more. So you always want to plot your data. So now, as we look back here, which one of these two graphs would have a smaller sum of errors, which means their variability from the line would be smaller? Well, you can see this one over here, all the points are closer to the line, so therefore plot B would have a smaller sum of squares. Here we're looking at the relationship of R and your slope. You know your slope's always the one in front of your variable, and it's positive. So therefore, we would conclude that R must also be positive. You could also make that conclusion by looking at your data and see that you're going up as you go to the right. Your R and your slope will always have the same sign, meaning both positive or both negative. And remember, your slope's always a number in front of x. So we want to go ahead, and if a person increases his or her weight by 10 pounds, how much would you expect their waist girth to increase? Well, there's a couple of ways you could do that. You could go ahead and figure out what it would be for, say, 140, and then also for 150, because that's going up by 10 pounds, and look at the difference in those two. That's one way to do it, and you would expect your waist to increase by 1.332 inches. What is our percent of variation in the y's? It can be explained here by our brother's heights when we're comparing our sister's heights. Well, we have an r here. Remember, your percent of variation or fraction of variation is always r squared. So you got to take 0.558 and square it. When you do that, you get 31% of the variability in the sister's height can be explained by the brother's height. The rest of the 100% from your 31% can be explained by other factors. So here we're given the correlation between our SAT math and SAT total, which is fairly high. Therefore, you would conclude What? Well, we only know that if R is positive, then your slope has to be positive. But R and your slope are almost never the same, so we know it's not A. What's going on here is we need to look at R squared, and that would tell us our percent or fraction of variation. If you take this number and square it, you end up getting a 0.987, or as a percent, 98.7. So we could say your math SAT explains about 98.7% of the variation in your total scores. Your residuals. Remember, your residuals are always your observed minus your predicted. The predicted is always the y hat. It's always observed minus predicted. Now, we want to use residual plots to basically magnify any false assumptions that we made or violations that we made. Now, here we have a residual plot. So which one of these two assumptions did we violate? Or neither? But there's a definite pattern in your residuals. So therefore, we would say it's assumption 1, that we cannot use a straight line. Which one of these do we use for prediction? Do we use our correlation or regression? Remember, correlation only measures your strength and your direction. Your regression is your least squares regression line, and that's what we use for prediction. Also, your regression line, remember, always passes through the average of the x's and averages of the y's. So what's the relationship between correlation and slope? Well, they always have the same sign. They're either both positive or they're both negative. What measures the strength of fit? And well, our strength of fit is R squared. Okay, sorry about that. I had a typo. It's really your correlation coefficient, and that's from one of the slides at the beginning of our lesson. Okay, causation. Taking a look here, reading through the problem, what would you conclude? Well, you would conclude that based on it being an observational study, you can't make any firm claims. And now we go ahead and look at our linear regression. We have our data down here for our diamond size and the carats. We want to go ahead now and make a prediction for a 1 carat diamond. What we would say is going on here is we would say that's extrapolation. We never want to do it, because keeping in mind that your data only goes from around a 0.1 all the way up to a 0.35, a 1.0 is significantly farther to the right, not in the range of your data.